All right, here we go. Last video, last assignments, and we're done for the year. So we're going to go to Dalton's law. All right, this one's a pretty easy one compared to the other ones because it's just adding and subtracting. So Dalton's law of partial pressure states that the pressure of a mixture of gases is simply the sum of the individual pressures of each of the gases, known as partial pressures. So let's say you're in a room. The air that's in your room is made up of a bunch of different gases. Oxygen, nitrogen, argon, water, carbon dioxide, a whole bunch of other ones. And so if I add up each of those pressures, that's how I get standard pressure for air, which is 101.3 kPa or 1 atm or 760 mmHg. So the equation you need to know is this one down here. The total pressure is equal to the sum of all the pressures. So if there's 6 pressures, I have to add up all 6 of them. So a type of problem you could see is like this one. A 5-liter container at 20 degrees Celsius has 4 gases pumped in. The total pressure, there's a key word right there, total pressure of the gases is 4.8 atm. If the pressure of the first gas is 1.2 atm, and the pressure of the second gas is 0.49 atm, and the pressure of the third gas is 0.78 atm, what is the pressure of the fourth gas in atmospheres? So let's write the equation. P total is equal to all of the pressure. So there's 4 gases pumped in, so pressure of the first gas plus pressure of the second gas plus pressure of the third gas plus pressure of the fourth gas. So let's plug them all in. I know that the total pressure is 4.8 atm. The pressure of the first gas is 1.2 atm. The pressure of the second gas is 0.49 atm. The third gas is 0.78 atm. And I don't know what this pressure is over here. So to calculate it, I can subtract 4.8 minus 1.2, 4.8 minus 0.49, 4.8 minus 0.78, or you can add them all up and then subtract at the end. Either way would be correct. So if I add them up, 4.8 atm is equal to, I think it is 2.47 atm plus the pressure 4. I would subtract 2.47, and so the pressure of the final gas, whatever pressure 4 is 2.33 atm. And that's it. That's the answer. Okay, you can run into a problem where they're actually different units. So here I have torr, atm, and kPa. So a container has oxygen, xenon, and helium. The total pressure, again, total pressure, that's when I know I'm using that equation, is 972 torr, helium is 0.458, oxygen is 74.1. What is the pressure of xenon? Okay, so same thing, P total, but this time instead of saying P1, I'm just going to say P of oxygen, which is O2, plus xenon, which is pressure Xe, plus helium, which is pressure He. So now I have everything. They want to know what is the pressure of xenon in torr. So when you plug it into here, you have to convert all of them to torr. So in this last problem that we did, they were already all atm, so I didn't need to do any conversions. Here, it needs to be in torr before I can plug it in. So the total pressure is already in torr, so I can plug it in right now. It's 972 torr. Oxygen, right here, here's oxygen. It says that oxygen is 74.1 kPa, so I need to change it to torr. So 74.1 kPa. This would be 101.3 kPa, and I'm trying to change it to torr, so 760 torr. In 3 significant figures, if I calculate this one, I get 556 torr. And there goes oxygen, 556 torr. I don't know what the pressure of xenon is, because that's what I'm trying to look for, so I'm going to keep it like that. Helium, on the other hand, I do know the pressure. Helium, it says right here, oh, it's spelled wrong, helium. is this in ATM? So I need to change it to torr before I can plug it in. So 0.458 ATM, 1 ATM, and 760 torr. Multiply these two because they're both at the top, and in three significant figures, I get 348 torr. Okay, now I have everything. I should be able to solve for XE now. All you need to do is take 972 minus 556 minus 348, and the pressure of xenon, if you calculate it correctly, should give you 68 torr. And that would be the answer for xenon. Okay, this one's a little tricky. It says a mixture of three gases is known to have a pressure of 1.27. If two of the pressures have the same partial pressure and the pressure of the third gas is 650 torr, what is the pressure of the other two gases in torr? So again, torr is my unit, so I need to change this one. I'm going to have to change ATM. P total is equal to the pressure of the first gas, pressure of the second gas, and pressure of the third gas. I also know that pressure 1 is equal to pressure 2. So instead of writing pressure 2 here, I'm going to put pressure 1, so that way I'll have two pressure 1s. So really the total pressure should be equal to 2 pressure 1s plus pressure 3, because they equal the same amount. So if I get pressure 1, I'm going to get pressure 2. All right, now everything needs to be in torr. My total pressure is not in torr, so I need to change it. So 1.27 ATM, 1 ATM, 760 torr, and that changes it to, I got 965 torr. So now I'm going to plug it in right here. 965 torr is equal to 2 pressure 1s plus pressure 3. This is already in torr, so 650 torr. If I solve, I'll end up getting, let's see, 315 torr is equal to 2 pressure 1s. So if I divide by 2, I'll get pressure 1, which was equal to pressure 2, which is now equal to 157.5 torr. And that would be the correct answer. Okay. Next, we're going to move on to ideal gas law. Okay, so out of all of the laws that we've learned, this is probably the most important one because this is pretty much what everybody uses. So you do need to know this one. I might not finish the notes because I just don't want to go over it and we're running out of time. So I'll probably stop after ideal. So we only have like 3 more problems to go. Okay, the ideal gas law is this right here, this equation right here. It is PV equals nRT. We call it Pivnert. So you have pressure times the volume is equal to the moles times R times T, which is a temperature. So I already know 4 of them. I know pressure, I know volume, I know moles, and I know temperature. The only one that I don't know, the new one, is R, which is the gas law constant. On this one, I'll give it to you on the test, or on the quiz, I'm sorry. And so on the quiz at the very top, I'll tell you what R is, but you have to be able to use R. Here is what R looks like. R is equal to the gas law constant. It basically makes both of these sides equal out. So the pressure and the volume will be equal to the moles and the temperature. So the number is 0.0821 liters times ATM, atmospheres, divided by moles times Kelvin. And R doesn't change. That is going to be the same R all the time. So we're just going to use this R with these units every single problem. Okay. Again, you don't have to memorize the units, but it's good to know how to use the units whenever you're calculating, because that's the big deal. So let's go to a type of problem where we'll actually be using it. So in order to figure out either if you're using Dalton's law or if you're using Pivnert, you have to look at the problem. If it says total pressure and it gives you a list of pressures, you're using Dalton's law. This one says how many moles, which is N, must be put in a 500 milliliter, that's volume. At 20 degrees, this is temperature. And 1.77 atm, that is pressure. Okay, so I have everything to see for Pivnert to solve for my moles. So PV equals nRT. I'm solving for moles, so to solve for moles, I'm going to divide both sides by RT. So PV over RT is equal to N. And now I just plug it in the order that it goes. So we'll start with pressure 1, or pressure, it's the only pressure. 1.77 atm. Make a table, and we're good. Times the volume, so the volume goes on top. It says 500 milliliters. Okay. Divided by R. R is going to always need its own column. So I'm going to put R here. Since I'm dividing by R, R is going to go at the bottom right here. It is 0.0821. If we go back to the units, so I'm going to go back to the previous slide, it is liters times atmospheres. So liters times atmospheres divided by moles times Kelvin. So divided by, remember this line right here means divided by moles times Kelvin. Okay, and there's my R. So I got P, I got V, I got R. Now I need temperature. I need to change the temperature because right now it's in Celsius. So add 273 and I get 293 Kelvin. And I can put it at the bottom. You can make another table and put it down here. It doesn't matter. I'm going to put it over here because I have space. So 293 Kelvin. The units do not need to match up. They only need to match up if I'm converting. I'm not converting here. I'm just plugging in these letters. Pressure's here. Volume is here. R is down here. T is right here. So I'm just plugging them in. Okay. Next, I'm going to start canceling out my units. So if I look, K cancels out, ATM cancels out. I'm left with milliliters, liters, and moles. Since they just want moles, I need to get rid of milliliters and liters. So I have to do a conversion step. Milliliters, liters. This is 2 letters, so this gets the 1. This would be 1 times 10 to the negative third. Multiply the top, divide by the bottom 2. And milliliters cancels out, liters cancels out, so you're just left with moles. So my final answer, if I plug this in correctly, it will be 0.0368 moles. And that's how to find how many moles of gas are actually inside the substance. Let's try another. So here I have a rigid steel container that has a volume of 20 liters, so volume, with 40 moles, so this time they give me moles, of nitrogen gas at 28 degrees Celsius. So there's my temperature. Let's add 273, 301 Kelvin. What is the pressure? What would the pressure be in kPa? So they're looking for pressure. So PV equals nRT. I'm trying to find pressure, so I'm going to divide by volume on both sides. So pressure is equal to nRT over V. All right, we're going to start plugging in some numbers, starting with N for moles. So here I'm starting for N, and it is right here, moles. So 40.0 or 40 moles. Okay. Times R. R again is 0.0821 liters times atmospheres divided by moles times Kelvin times the temperature, which is 301 Kelvin, divided by the volume. Again, I can put the volume here or I can put it here because I'm just plugging them in. I am not converting. So I'll put it here. 20.0 liters. All right, they want the pressure in kPa, so I just need to cancel out my units and make sure I have kPa. So mole, K, liter, liter. I'm left with ATM, that's not kPa. So one more step, conversion, ATM to kPa. Know your conversions. 1 ATM is 101.3 kPa. Multiply the top, divide by 20. I got 5,007 kPa. If I wanted two sig figs, I could have put 5.0 times 10 to the third kPa. Same thing. But your quiz is multiple choice, so you don't have to worry about significant figures. Okay. Is this the last one? No, two more. Okay, how many moles in a 500 milliliter container that exerts a pressure of 2500 mmHg at 350 K? Try pausing the video and try doing this one on your own. Okay, if you got the answer 0.0572 moles, then you're good. You can just skip ahead and go to the next question. If not, watch the video. So PV equals nRT. Let me label stuff. This is volume, this is pressure, this is temperature. Okay, I'm looking for moles. So I'm going to divide by RT on both sides. So PV over RT equals N. Starting with the pressure, 2500 mmHg. Times the volume, 500 milliliters. Divided by R, remember R needs its own column. Divided by temperature, I'm just gonna put temperature on this one, 350. Okay. Okay, they want moles, so the only unit I want to keep at the end is this one. Everything else should cancel out. So let me try to cancel out everything. K. All right, that's it. So since that's it, I need to convert mmHg and ATM. Since they're both pressures, I can do a conversion step. ATM, mmHg. 1 ATM is 760 mmHg. If I do that, then mmHg now cancels out, and so does ATM. I still have liters and milliliters though, so I need to do another step. I want to get rid of liters and milliliters. 1 milliliter is 1 times 10 to the negative third. And so milliliters cancels out, liters cancels out. Okay, now everything's canceled out except for moles, so then you plug it into the calculator. So you only plug it into the calculator when you only have the unit you're looking for. If you plug it in, you should get 0.0572 moles. Okay, try pausing the video and try giving me an answer for this one. Okay, on this one, if you got letter D, then you are good and you understand everything and you're ready for the practice and the quiz. If not, keep watching the video. So I have Pivnert. I'm looking for pressure. So I'm going to divide by volume. So pressure is equal to nRT over V. All right, in this problem, I don't have moles, but I have grams, and I can convert grams to moles. They're basically the same thing. So this would be my moles number then. 36 grams of helium times R, 0.0821 liters times ATM divided by moles times Kelvin. Temperature, 10 degrees. So here's my temperature. I'm going to add 273, so 283 Kelvin. Divide by the volume, 5.00 liters. So if I cancel everything out, liters cancels out, K cancels out. All right, I'm left with grams, moles, and ATM. I only want to keep ATM, so I need to get rid of grams and moles. So in this next step, I'll get rid of grams and moles. Grams and moles. Well, you should know for every 1 mole is the molar mass. So if we're talking about helium, if you look on the periodic table, helium's mass is 4.00. And so grams now cancels out, and so does moles. Now I only have ATM. If I plug this in, multiply the top, divide by the bottom, I should get 41.8 ATM. And that's your answer. And we're done. No more videos. Congratulations.